Okay, so welcome to this first module video. This module is about atomic sentences, but equally as important are also terms and, in particular, complex terms. Okay, so we've got sort of six main learning objectives for this particular module. The first is to be able to identify when an expression is an atomic sentence in a general first order language. And here, what I mean by an expression is just some random string of symbols. And what we'd like to be able to do is if we write down some sort of sequence of those symbols, can we identify if it's an atomic sentence? The same thing true for terms, and in particular complex terms in a general first order language. And notice I'm saying general here because it really sort of depends on how you specified your language. So first order logic is a collection of languages, and you have to specify the details of that language before you can get sort of started. So here, whether or not something is an atomic sentence or a complex term or a term will depend on how the first order language has been specified. And that'll also have some bearing on how we translate between sort of colloquial English and atomic sentences of general first order language. Now, typically, one direction is really straightforward. Going from the first order language, the very precise language, back to English is typically pretty straightforward. You just look at the interpretation and sort of write it out in regular old English. But going the other way around can be difficult, and often it's easy to write down something in English that your particular language won't be able to express. But we'll get some more practice with that throughout the semester, and ideally you'll be fairly good at sort of going back and forth between regular old English and these first order languages. The fourth thing is probably the most important here. You should be able to compare and contrast the following three objects from first order logic. The notion of a constant symbol, a predicate symbol, and a function symbol. Sort of how are they same and how are they different? And we'll say a few words about that on some subsequent slides. The fifth here is to be able to construct terms and atomic sentences in the first order language of set theory. So we'll talk a bit about set theory. And there's a bit of a mistake here. It turns out that the way we'll define set theory in this textbook is to be sort of termless. So there won't be any terms at all. And it'll make it sort of difficult to write down atomic sentences. But I'll say a few words about that. And then we'll look at the first order language of arithmetic, which will include function symbols. And the book here is intended for a pretty wide audience, but it does a pretty poor job with function symbols. And so we'll talk about them in a bit more detail because for mathematics, the notion of a function symbol is particularly important, especially in algebra when you're talking about groups and rings and various things along those lines. So we'll talk a bit about the language of arithmetic, which is also the language of doing something like number theory. Okay, so just as a quick reminder, I am assuming that you've already completed the reading assignment at this point and are familiar with the contents from Chapter 1. So we'll sort of be summarizing as we go along, as opposed to sort of taking this as an introduction to the material. Okay, so I'll focus a bit on this learning objective about comparing and contrasting constant, predicate, and function symbols, and I'll remind you of some of the sort of important facts at the end of the various sections of Chapter 1. For example, here in this section, on constants, there's a reminder at the end that in FOL, or first order logic, every individual constant symbol must name an object. Okay? And often we'll use just single lowercase letters but sometimes we'll use sequences of letters, like a name, like I think they use Max or something like this. And no individual constant can name more than one object. So if you have a constant, it refers to at most one object. And then finally, an object can have more than one name or no name at all, right? So there could be objects in your world or in the setup here that just are not named by any sort of constants in our system. And furthermore, you can take some object and it might have two different names or two different constants that name the exact same object. So, for example, you may go by a name and then also go by a nickname or maybe a shortened name or something like this. And that would be sort of similar to that situation. However, notice in the real world, you can have two people that have the same name. And here we're explicitly sort of forbidding that possibility with the idea of a constant. Okay. Okay, so let's now jump to the idea of a function symbol, which the textbook sort of waits till the end of chapter 1 to talk about this, but I think we'll sort of bring it up here a little more quickly. But function symbols work a lot like constant symbols in the sense that they name sort of objects in the world that we'll be looking at, or in whatever we're trying to describe with our particular language. And each function symbol, like a predicate symbol, will have an arity. And we can form what we'll call complex terms by putting a function symbol of arity n in front of n other terms, either simple or complex. And so this is sort of a recursive definition, and you can repeatedly apply these function symbols to come up with complex terms or other names. And, a good example of this occurs maybe when you're sort of dealing with kids or something like this. For example, I have a 3-year-old and a 7-year-old daughter. And often when they're playing with other kids, they'll refer to sort of parents as the mom of such and such or the dad of such and such. And they're really just sort of using a function symbol there, right? So instead of just referring to them by their actual name, they've referred to them as this sort of constant function being, dad of or mom of, and then the name of the child, right? But it happens quite often in mathematics that we use sort of function symbols. They're not exactly the same sort of functions you might have seen in maybe a calculus course or a differential equations course, but sort of more related to naming objects in our environment. And like it says here, that second one, complex terms are used just like names in forming atomic sentences. And so it turns out that you could, in essence, remove function symbols altogether by sort of just adopting a constant term for any thing named by a function. And so that's why the book itself doesn't really go into as much detail as I would like. But it turns out that in mathematics, right, and so lots of applications in mathematics, these function symbols are incredibly important, especially in things like algebra, where you look at groups and rings and things like this. So we'll try to bring it a little more to the forefront here. And then I'll point out again sort of that last term there. In first order logic, complex terms are assumed to refer to one and only one object, right? So just one. Okay, so finally, let's circle back around to the notion of a predicate, which is very similar to the idea of a function symbol in the sense that they both have arities. And the way in which we form complex terms is analogous to the way in which we'll form what are called atomic sentences. So if we take a predicate of arity n and place it in front of n names enclosed in parentheses and separated by commas, then we obtain what is called an atomic sentence within our first order language. And we'll try to stick to the convention of when we name predicates in our first order language of using a capital letter. And this is a bit backwards with sort of regular English. Often we use for sort of names that name people a capital letter, but here we'll use capital letters for predicates, and constants and terms and things like this we'll use lowercase letters. So it's clear the distinction between a function symbol and a predicate symbol. Because again, notice that the way in which you build up atomic sentences is in essence the same way that you would build up complex terms from function symbols. Atomic sentences are also built up from the identity predicate. And I should point out that it is sort of the one symbol that is taken to be the same interpretation in every first order language. And we also will use a slightly different notation for it, the infix notation, as opposed to putting like an equal sign and then parentheses with two names and a comma, like we would for other predicates. And it's always the case that the equality symbol is to be interpreted as the two things on the left and right hand side of the equality symbol naming the exact same object, right? So there'll be some sort of complex term on the left side of that equal sign and a complex term on the right side of that equal sign. And those predicates will be true precisely when they're the identical or same objects in that particular setup or whatever it is that we're sort of trying to describe with our first order theory. And it's important to point out that for these predicates and for these atomic sentences, and the same thing is true for complex terms, the order of the names is incredibly crucial, right? So depending on the interpretation of the predicate and whether or not it's sort of true or false, can depend upon the order in which the names appear within those particular predicates. Okay, so just maybe circling back around here for a moment, let me point out four things that I think are important about first order languages here. First off, whenever you're designing or specifying the details of one of these languages, you must specify all of the constant symbols, function symbols, and predicate symbols, along with their arities, before you start doing anything. And as soon as you do that, all of the complex terms and what they sort of reference to, and all of the atomic sentences can then be sort of constructed from that information. Depending on what you take for those symbols, you may or may not be able to express everything that you would like to in sort of regular colloquial English. But when you're specifying or designing one of these languages, what you want to express is sort of the content of whatever it is that you're trying to investigate. The second is just something I said earlier, but I'd like to remind you again. We'll try to follow the convention of using lowercase letters for constant symbols and function symbols, even though they name things, and reserving a capital letter for predicates, right? And the idea here, making it easier for you to read through and see that, oh, okay, this is a predicate, and so therefore this statement is an atomic symbol, or I'm sorry, an atomic sentence. And remember that atomic sentences are sort of the most basic sort of expressions that we can say about the objects that we've named in our language. And so, again, this convention will help us sort of distinguish between what we're using with function symbols and what we're using with predicate symbols. The third here is just a reminder that both predicate and function symbols have arities, and those are used to construct atomic sentences, and function symbols are used to construct complex terms. Finally, the book does a sort of a poor job of emphasizing the use of function symbols because, again, it's sort of a wide audience here. It's more than just maybe graduate students in mathematics course that they have in mind. And so we'll be sort of focusing some of our attention in the course and in some of these videos on remedying that and talking a bit more about function symbols. Although I'll remind you as well that they are sort of not necessarily important because every thing that's named by some sort of function symbol could have just been introduced as a constant when we were designing our language. Nonetheless, they'll be very important in mathematics. Okay, so some excellent examples of languages from first-order logic that'll be important for us are the first-order language of set theory and the first-order language of arithmetic. And as I said before, the first thing that we really should do here is specify exactly what sort of constant symbols, function symbols, and predicate symbols we'll be using in these particular languages. And again, these are probably among the most useful of the languages that we'll see in the course. However, in order to gain a better sort of footholding and a better understanding of the material from sort of logic, we'll also be using an interesting language called the block language. So we'll talk about that first and then come back to set theory and the language of arithmetic. Now, the really nice thing about the block language is that there is an entire program, Tarski's World, that goes along with sort of understanding and working with the details of that particular language. And a lot of the exercises that we'll do throughout the semester will involve this particular language. So here is a nice picture of the program that you can install on your computer if you download it for sort of Windows. But there are also versions of this that you can run in a web browser. And here in a couple slides, I'll show you some of the details and how to sort of navigate. And we'll talk a bit about the block language and when atomic sentences, are true or false in that particular block language. And then we'll sort of cycle back around to set theory and arithmetic. Okay, so the block language is fairly straightforward, and the first thing I should do is sort of specify exactly the details of the various types of symbols. The first thing to maybe point out here that you don't see on this slide is function symbols, and that's because the block language and its sort of form for Tarski's World doesn't contain any function symbols. However, there is at least one homework exercise where you'll be asked to add some function symbols to this particular language, and then even something where you'll have to sort of submit it sort of electronically. So the textbook does sort of discuss how you could add some function symbols to this particular language. But for the remainder of the semester, we won't sort of take that as sort of being part of the block language. Instead, we'll assume the block language doesn't have any function symbols at all. For constant symbols, it has 6, just lowercase letters, A, B, C, D, E, and F. For predicate symbols of arity 1, there are 1, 2, 3, 4, 5, 6. There's tet, dodec, cube, small, medium, and large. There's quite a few predicate symbols of arity 2, larger, smaller, same size, same shape, same row, same column, adjoins, left of, right of, back of, front of. And then, as with all first-order languages, there's that predicate symbol of equality. And symbols of arity 2 are also called the binary predicates. And there's only one predicate symbol of arity 3. And to form an atomic sentence with that, you would actually need to place 3 terms to the right of it, separated between parentheses and separated by commas. And so in this case, that predicate symbol is between. Okay, so what you're seeing here is the course resource page for the textbook, and I've clicked on the application tab. And here again, you'll see the 4 programs that we'll be using for the course. And today we'll be talking about Tarski's World. You can also click on the downloads and download it and install it on either a Mac or a Windows. But if you just click on this button here, you can run it directly in your browser. And it looks basically something like this. Let me clear off this board real quickly. If your board isn't cleared, you can always grab some of these blocks and just throw them sort of over the edge, and it'll clear them off. So there, my board is sort of cleared off. And this is what Tarski's World sort of looks like. And we've talked a bit about the various predicates and constant symbols for the block language. And now we'll be talking about how we determine when a given atomic sentence is either true or false. And it really depends on the world that you're trying to describe. And in the blocks language, we're describing various worlds that are on a grid, black and white grid, like the one that you're seeing here on the left. And that world is populated by various types of blocks. So you can see these 2, for example, cubes here. And you can get sort of a view from above. And each one of these objects that you place down, you can change its properties. So for example, these 2 cubes, I can move the column or sort of the row on the grid that they're on. And that'll have a bearing on whether or not some of the atomic sentences are true or false that we write down sort of later on. Some of the other properties that we can modify in this picture here are the actual shapes of the objects. So if, for example, I click on this cube, I can turn it into a tetrahedron if I would like, or a dodecahedron. And I can also modify the size. So there's the small size, which is currently its current format. There's a medium-sized sort of object, and then there's also a large, and that's true for all 3 of the various shapes. So you can continue to add blocks, as many as you'd like, 1 for every position on this particular grid, and then you can go through and change the various properties of these particular blocks. And based on the configuration that you set up here in the world, the sentences and the atomic sentences that you write down here on the right-hand side will either be true or false. And Tarski's World has a nice sort of an evaluation system here for determining if a given sentence that we've written down is either true or false. The only other thing that you'll need to sort of know here is what these lowercase letters represent, and these are constant symbols. So these are the symbols A, B, C, D, E, and F, and they reference, or they should reference, in our particular world. And you can assign a given object one of these constants. So for example, if I click on this cube here, and then I click on the constant A label now shows up down here, and this tells us that that constant A is now referring to this cube. And once we use A to refer to this cube, we can't use A any longer to refer to any of the other objects, and that's because constant refers to 1 and only 1 object. However, we can take the same object, the object here represented by A, and give it another name. For example, this means that the object named by A and B is this exact same square. Okay, and so we can form sort of interesting atomic sentences over here and ask ourselves if they're true. And in fact, we can even just sort of click on the evaluation button above to determine if they are. Let's start with an example of a one-array predicate. And there are sort of 6 ones to choose from. So there's tet, cube, dodec, small, medium, and large. And in this case, since we have only looked at the constants a and b, those are the only things that are sort of naming things in this case, we can look at a sentence, for example, like the following: the predicate cube, and then it's a one-array predicate, so we need to put a term in here. That's 2 parentheses, and then that term for a. And this sentence will be true if the object that the constant a is referencing is actually a cube. And in this particular case, you can see that from our setup, it is. And if we ask Tarski's world to evaluate this evaluation button here at the top, it'll come back with a T telling us, yes, indeed, the constant named by a is a cube. On the other hand, we could use the other predicate, tet, for example, of a, and tet a is just saying that the object is a tetrahedron. And clearly, it's a cube, it's not a tetrahedron, and if I hit that evaluation button here, I get an F telling me that doesn't, or that's not true. On the other hand, if you have constants that are sort of unused, for example, F isn't labeling anything, I can write down an atomic sentence, but it's still, its truth value can't be determined. So for example, if I ask, is F a dodecahedron, and I sort of spelt this wrong here, we put dodecahedron, try to evaluate that, it will basically tell me, I'm not sure exactly what you're talking about here because the constant F hasn't been assigned to any object, so it doesn't know if it's a dodecahedron or not. However, if I click on one of these objects and, for example, name it F here, that dodecahedron, well, then I can hit the evaluation button here, and you'll see that, aha, okay, it is true that F is now naming a dodecahedron. On the other hand, if I remove that label and make this cube the dodecahedron, I'm sorry, this cube here, the object that the constant F names, and then I can evaluate, notice that it's false. The button next to this is evaluate all, and it just takes all of the sentence that you wrote down and evaluates whether or not they're true. So in this case, the first one's saying that, yeah, it's true that A is a cube. The second saying that it's false that A is a tetrahedron, and the third is saying that it's false that F is a dodecahedron. Okay, and we're not only interested in one-array predicates, but two-array predicates, and those are also called binary ones. And there are a lot of binary predicates in this case. So there's same shape, left of, right of, front of, back of, same column, same row, adjoins, smaller, same size, and larger. Let's start off with, for example, just same size really quickly. It's a binary predicate. So here we have same size. Notice I started it out with a capital letter because we're sort of following that convention that predicates start with capital letters. And because it's a binary predicate, between these parentheses, we need two terms separated by a comma sign. And the order of those terms often will matter, not always, but will often matter. And in this case, we can ask whether or not the object named by A and the object named by F have the same size. If we come up here and evaluate, the answer is that they indeed do, and that's because right now they're both marked as having the property of being small. Now, if I were to take this one over here and make it large and check the same sentence again, you'll notice that indeed it's a false sentence. Okay, one thing to point out here is that the orientation of the board can have some bearing on whether or not some of these predicates are true. So for example, if you change the orientation of the board, whether or not one object is to the left of or the right of or in front of or in back of, in front of means sort of lower down on the screen here, that can change, right? So make sure that you keep that in mind as you're sort of rotating the board around. And then finally, the last is this three-ary predicate, and that means that when you're forming that atomic sentence, instead of just two terms, you'll need three terms. So let's look at between, and let's say in this case, we'll look at A, B, and F. And let's just evaluate it and see what it tells us. In this case, it's false, and that's because in this case, the thing named by A is not between B and F. But let's go ahead and make sure that this is no longer labeled A. So let's come to this object and remove that label A. And then here, I'll label this one now A. And I'm going to slide these so that they're sort of in the same row here. And now you'll notice that the object named by A is in between the object named by B and F. And if we evaluate that sentence, then we see in this case that it's true. So whatever that first constant term is, it's in between the two terms that are named by B and F. The last sort of thing that I want to point out here on this setup is if you come up here to the top where it says file, you can open files, and you can also open and update worlds and that sort of thing, and you'll need to do that in order to get some of the homework assignments done. All right, now that we've talked a bit about the blocks language and Tarski's world and how to determine whether those atomic predicates, atomic sentences are true or false in that block language, let's now go back to the language of set theory and the language of arithmetic. And again, the most important thing is that you specify clearly what your symbols are. And the nice thing about the language of set theory is that it is very minimalistic. There are absolutely no constant symbols. There are no predicate symbols of arity 1. There are no predicate symbols of arity 3 or above. And there are only two predicate symbols of arity 2. There is the equality symbol, which is common to all first-order languages. And again, just means that they're identical. And then there's this stylized Greek letter epsilon, which means is a member of, or reads off as a member of. And that's it. So that's the only two predicates. And in fact, the equality symbol is unnecessary here. If you look at the axioms of set theory carefully, you can define equality of sets completely in terms of this one membership symbol. So there's only one symbol. But notice that means that in our current setup, there are no atomic sentences for us to consider because we don't have any terms at all. So there's nothing for us to even sort of reference. But we'll come back to this language of set theory when we start talking about quantifiers, because that's a case where we won't need to necessarily have any constants or terms, but we'll introduce variables and talk about whether or not some property holds for all possible objects within our given universe that we're trying to describe, or if there exists maybe one object in our given system. So we'll come back to some of those, but again, that language of set theory is pretty straightforward. However, there is an exercise in the homework that asks you to determine if some sentences in the language of set theory are true or false. And in that case, it'll introduce some constant symbols. And in this next slide, I'll give you a little bit of information about that question. And it'll require you to have some knowledge of sort of naive set theory, so that you've already seen a bit of set theory. But I'll talk a little bit more detail about how to solve that one in the next slide. Okay, so here's the exercise 1.19 from the textbook that asks you to determine if some atomic sentences in the first-order language of set theory are either true or false. Now, it's important to realize here that they've added in some constant symbols. So this isn't exactly the same language of set theory that we had mentioned in the previous slide, but instead, we've added in a few constant symbols. And in this case, they have symbols for A, B, C, and D. And in this case, C is a name for the number 6. And D is a name for this sort of complicated set here consisting of 2, 7, and then the set 2, 4, 6. Now, it doesn't say it here, but when it says above, it's referencing the textbook. And in this case, A is referencing the number 2, and B is referencing the set containing 2, 4, and 6. Okay, so just maybe written out here in a slightly odd notation that's not in first order logic, but more in sort of the notation of naive set theory. We have the following. Again, A is 2, C is 6. B is a set with 3 elements, 2, 4, and 6. So this is the set builder notation. And then D is a set with 3 elements, 2, 7, and then the set B itself. So notice, for example, that 4 and 6 are not elements of D. On the other hand, A is an element of B, and so on and so forth. And based on this information, you should be able to determine if these 6 atomic sentences are true or false. Okay, so now we're on to another important language, the language of arithmetic. And this is often what's used in the study of number theory. Here we've got 2 constant symbols, 0 and 1. Notice the number or the numeral for 2 or 3 or 4 that we might be used to are not symbols in this particular language, just the symbols 0 and 1. So we really only have names for 0 and 1. We don't have any function symbols of arity 1, but we do have function symbols of arity 2. And in this case, they're the addition symbol, the plus sign, and the multiplication symbol. That's that cross that you're seeing there. And we can build up complex terms using these function symbols of arity 2. Now, when we are using these function symbols of arity 2, just like the textbook mentions, we use infix notation, similar to the way that we use equality on the inside. So we put a complex term to the left of the plus sign and to the right of the plus sign, or the left and the right of the multiplication sign, and we end up with a complex term. And I'll summarize that again on the next slide because there's some really interesting homework exercises related to that. And then also the discussion for this week is as a component related to this language of arithmetic. Okay, and again, the numeral that we would normally write down for 2 is not a symbol in this particular system. However, we can obtain a complex term for it by, for example, taking 1 and adding it to itself. So 1 plus 1 would be a complex term that would reference that number 2. And there are many different complex terms that reference the same symbol, like that symbol number 2. And again, that'll be part of the discussion and the homework assignment as well. Okay, so again, the constant symbols and the function symbols allow us to construct terms and complex terms, and those are sort of names for objects in our system. And in this case, the sort of objects that we're looking at are not sets or blocks, but instead just whole numbers or integers, right? Positive integers in this case. And so we'll want some predicate symbols to tell us whether or not there's a relationship between or what sort of properties these numbers have. In our system, we'll have no predicate symbols of arity 1 or arity 3 or above, but we will have binary predicate symbols or symbols of arity 2. There's always the equality sign, and then in this case, with the language of arithmetic, we also have the less than relation. So again, you put two complex terms, one on the left and one on the right, or just regular terms, one on the left and right of these symbols, and you obtain an atomic sentence. And whether or not the number on the left is smaller tells you if the sentence is true or false for that second predicate symbol. And if they're the same object, or if they're naming identical objects, then they're true for the equality symbol. But again, that equality symbol is the same across any and all first order languages. Okay, so here I've taken a screenshot from the textbook of the definition of terms, in this case complex terms, for this first order language of arithmetic. And here it's sort of specialized for the various constant symbols and function symbols that we have, right? So notice there are essentially sort of three rules. The first is that 0 and 1 are terms. And again, those are terms because they're constant symbols. We specified them at the very beginning. And then the second rule is telling us that, okay, if you hand me two terms, right, and they could be very complicated expressions. You hand me two terms, say T1 and T2. Well, I can put parentheses, the first term, T1, an addition symbol, the second term, T2, and then another parenthesis, and I obtain a new term. And I can do the same thing with the multiplication symbol as well. And I'll get a new complex term. And you sort of do this in an iterative process, right? So it's sort of, you're getting more and more complicated terms as you apply rule number 2 over and over and over again. And it turns out that these are the only ways to form any of the terms, or the things that actually name objects in this first order language of arithmetic. So let me give you an example. So here is a complex term that's been built up by repeatedly applying these rules. First off, we note that 1 is a term, and therefore we can form 1 plus 1 with parentheses on the left and right. And that would be applying the first rule and the second rule once. So 1 plus 1 with those parentheses is a term. And then because 1 plus 1 with those parentheses is a term, we can then apply that rule again, but instead of using addition, using multiplication. And we end up with this expression down here. So these opening parentheses, and then we've got 1 plus 1 times 1 plus 1. And if you think about what the interpretation of that really is, this is the same thing as 2 plus 2. So this is really sort of a name for 4. Notice that we couldn't use the numeral 4 here in this particular system because it wouldn't even be a symbol in our system. However, this is a complex term in our system that does refer to 4, and there are many others that refer to 4 as well. But I wanted to talk through that sort of process here because in the textbook there's an exercise where it asks you to sort of trace out that process of which rules were used to construct some of those terms. And in the discussion, I'll also ask you to identify sort of your favorite number and then try to write it in various formats or express it using some of these complex terms in this first order language of arithmetic. And again, I'll remind you that you can't use things like the numeral 2 or the numeral 3 or the numeral 4 for in this case. Instead, you'll want to use these function symbols to build up terms that reference those things.